going to the end, so it's the last session of this workshop. So the first speaker is David Kaplan. He's going to tell us about cosmological relaxation theory and experiment. Let's welcome him.
Hi, good morning. Whoa.
Relax.
Very, very nice to be in Taiwan. First time. And thanks to the organizers for organizing a very nice conference. I'm going to talk about a proposal for a solution to the cosmological constant problem, and some of the details, some of the phenomenology at the end will be a little bit more general in the sense of the kinds of things you might look for cosmological relaxation. The cosmological constant, of course, at least written in the action of the Einstein-Hilbert action, there's gravity, GR, which is just the Ricci scalar. There's the standard model Lagrangian and the couplings to the metric that are required by diffeomorphism invariance. And then, of course, you can write a constant times the square root of minus g, and that's allowed by diffeomorphism, and that is, in fact, then a contribution to the cosmological constant. There might be additional contributions to the cosmological constant from regular matter, and so ultimately we will produce an equation of motion for gravity, which looks like Einstein's equation, and it includes some constant. Let's say we extract the piece out that acts like the metric times a constant, and we call that the cosmological constant. That's the thing that has the distinctive impact on how the universe evolves. Here are Friedmann's equations, and we see Friedmann's equations where we extract out what we mean by the CC. This is a constant which appears in the h squared equation and not in the h dot equation. And so in the limit where the cosmological constant is dominant, and by the fact that it's a constant, eventually at some time in the history of the universe it will become the dominant energy density, then we see that h is a constant, and the solution to the expansion a, the scale factor of the universe, is just an exponential. And so with the sort of standard initial conditions, you have an exponentially growing universe, and we have something that appears to look just like that. Now, what should the value be? Well, the value is corrected by all kinds of quantum loops, because it's a full quantum field theory at energies well below m Planck, and so we can calculate those contributions. Divergent they are. The standard model doesn't tell you how to make these things finite. There are finite contributions that depend in non-analytic ways on the parameters of the standard model. There's a bare contribution, and there are other contributions which can happen, say phase transitions during the evolution of the universe, et cetera, et cetera. All of this garbage falls into contributions. And if you believe all of this work and the standard model up to the Planck scale, then you estimate, at least naively, cutting off the divergences, something which is way too big. And that's the cosmological constant problem. And so the most popular explanation is that it's anthropic, that the universe looks more like this, in the sense of there are sections where locally you would describe the energy-momentum tensor as having something like the cosmological constant, and there are very tiny regions, if you can say something about relative sizes in an infinite universe, that has a tiny enough cosmological constant that allows life to exist. And famously, Weinberg suggested that this is a reasonable explanation after the fact, and that the numbers you get roughly correspond to requiring structure to form in our universe. This assumes that everything else is constant. In other words, that we take all of the aspects of our cosmology, the initial conditions of delta rho over rho. Once we do that, we roughly, sort of, within a few orders of magnitude, get the right cosmological constant. And this is, in a sense, a historic solution, meaning it involves the entire history of the universe, or a large chunk of the history of the universe, and that some part of the universe will look like ours today, just by accident, but statistically probable if we have a way of describing statistics on this space. So we have a model which is in a sense a historical model. It says it has to do with how the universe evolved, but it does not require anthropics. And I will describe that today and the consequences of it. So here's a plot. This is the size of the universe with some scale factor normalized to something. And this axis is time. And so in our model, we describe the evolution as follows. There's a long period of cosmological constant domination. And with it, there's some field which is rolling down a very flat potential. And so for a long period of time, the cosmological constant is the dominant energy density of the universe, and the kinetic energy of this rolling field is subdominant. But at some point, that stops, and it turns out to be a point where the cosmological constant is very small. Then the field can continue to roll through zero, because there's nothing special about that point at zero. And as it rolls through zero, the expansion rate, h, goes through zero itself and becomes negative. So a universe that has a cosmological constant which goes to a negative value starts to crunch. It continues to crunch, and the cosmological constant part, the vacuum potential part, does not blue shift, but the kinetic energy of phi blue shifts, and you get a kinetic energy dominated universe. We couple phi to other fields in such a way that at some point phi kinetic energy decays into radiation. Radiation that includes the standard model, and now the universe is dominated by the standard model, but it is crunching. And so all we need to do is turn around the direction of the universe, and so somehow magically the universe needs to bounce. And what ensues afterwards is Big Bang cosmology. And now I'll describe in detail each of these sections and how we get from one to the other, and eventually with the goal of being normal Big Bang cosmology, but with a cosmological constant tuned at much earlier times and remaining roughly the same by we get to the end of this story. That's what's happening with the universe. That's the scale factor of the universe.
But you end up with positive CC at the end.
In that little story, we end up with a tiny negative CC, but we'll see.
There's a little problem with that.
There's a little problem, but it's little, and we'll talk about how to fix it up. So looking at a field that is rolling, let's start with a very simple model, which is a field with a linear potential and a arbitrary cosmological constant. Now, the field has linear potential, but we're just expanding the potential around some region of the potential. So it's much more generic. You can imagine that this thing has a minimum somewhere at very large negative cosmological constant, and we're focusing on the rolling as you approach zero. So the summary is phi rolls slowly due to Hubble friction for an extremely long time, and the cosmological constant drops. There's a critical point at which the field vacuum energy and the Hubble rate is so small that the friction no longer can keep it slowly rolling, and phi begins to fast roll. The kinetic energy and potential energy are roughly the same. That's the critical point. And it fast rolls through zero, and once it goes negative, the universe very quickly starts to crunch. As it crunches, the kinetic energy blue shifts and becomes the dominant energy in the universe. And after some time of crunching, that kinetic energy is converted into radiation, and the radiation due to friction stops the rolling of phi. What we'll find is that this distance that it rolls is not significant, and that a tiny cosmological constant, say, that we start with here, is roughly of the same order of magnitude when the entire rolling ends. At this point, a bounce must occur because the universe is contracting. We need it to be expanding, although this mechanism that mostly I'll describe is independent of how the universe bounces. And at the contraction and the expansion, phi freezes in the sense that Hubble is now so large, but this slope is so small, that phi is not rolling and only starts to initiate rolling today, giving you some cosmological predictions. So here, this will be a little cartoon of the evolution of the universe, and we'll focus on what's happening with phi. So first, I write down my potential at some slope, and I want to start at as large as cosmological constant as possible. But if I do that, I have a constraint if I don't want quantum fluctuations due to Hubble to dominate classical rolling, and that gives me a limit on how shallow this slope can be, which is related to the Hubble scale at the very top. The Hubble scale at the top is dominated by vacuum energy, and so this puts a bound just on this slope parameter g. G is greater than lambda squared over m Planck. As you roll, you get down to a point where fast roll begins. Where do the slow roll parameters break down? They break down in, say, linear potential, for example, when you're a Planck length away in field space from 0. We'll talk a little bit about, is it okay to be many, many Planck lengths away from 0? But let's just start here, agnostically, and we get to the point where you start to fast roll. That point, we want to be our small cosmological constant. We set that, let's call it lambda 2 to the 4th. Now we have this relationship and this constraint, and now we have a relationship between the upper limit of what this cosmological constant can be, the initial one, to the tuned one. And that limit is this geometric relationship between the two. And so if we want today's cosmological constant to be milli-eV, then this simple model can solve the cosmological constant problem, starting with cosmological constants of capital 10 MeV, or 10 capital MeV. This type of model, or some other version of this model, is originally suggested by Abbott and Banks in the mid-80s. And the serious problem with those models is they suffered from eternal inflation and an empty universe. We've avoided eternal inflation, but we do still have an empty universe at this point. The next thing that happens is, because phi is fast rolling, it rolls to a negative cosmological constant. And so then you can see quickly how quickly does the universe start to contract. It starts to contract when Hubble changes sign, or when h squared goes through 0. That's when the kinetic and potential energy are roughly the same magnitude, and now the potential energy has gone negative. We see that h dot, the change in h, is of order of the kinetic energy. And since these two are roughly the same, in a Hubble time, Hubble changes by order 1, which means in a single Hubble time, the universe starts to crunch. The Hubble parameter hits 0 and runs negative. And so at a finite value of phi, and it's roughly of order m Planck, the universe is starting to crunch. Now as it starts to crunch, phi dot, that's kinetic energy, you might worry that that blue shift of the kinetic energy may get phi to roll very quickly down this slope. But as the universe crunches, the Hubble scale magnitude is going back up. So things are happening faster and faster. And so you can calculate how far does phi roll down as a function of how much I crunch the universe. Well, kinetic energy, when it is dominant, kinetic energy goes as 1 over a to the 6th. So phi dot, the value of phi dot, will go as 1 over a cubed. And so if you want to calculate how far does phi travel, you integrate dt phi dot. You can convert time into scale factor. You can convert a dot into Hubble. And when you then do this calculation, compute with Hubble and phi dot, both going as 1 over a cubed, you get a log of the scale factor times the overall m Planck. And therefore, the distance that phi rolls, even if the scale factor changes by an exponential amount, is some numerical quantity, let's say of order 100. And so the distance that phi rolls is not significant compared to this, say, long distance up to a large cosmological constant. So you can crunch to extremely small scales and still have your cosmological constant well within this tiny range. And now you want to do two things. You want to stop phi, and you also want to take all that kinetic energy and dump it into the standard model. And so this is going to be one of the messier slides, and I apologize. But This is a version of a model that should do the trick. If we couple phi to various gauge fields, say a U1 field and a Yang-Mills group, then a coupling to a pure Yang-Mills group has been shown in thermal field theory to create a friction on a rolling scalar field with this axion-like coupling. And that friction goes as T cubed. And so the friction goes into the equations of motion for phi, and this gamma then is absorbing the kinetic energy and dumping it into this thermal bath. When that friction is much larger than the Hubble friction, you can easily estimate that the phi dot energy dumps itself into the T to the fourth energy density, the temperature bath, and this is just runaway behavior. It runs phi dot to 0, and in which case, in almost all of the kinetic energy is dumped into the thermal bath in a time scale of 1 over that thermal friction term, that rate, which we've taken to be faster than Hubble. This all works as long as that F coupling is less than alpha cubed T reheat M Planck. That gives you the temperature at which this happens. You want to know, now we've made this starting point, which is that the friction starts at some non-trivial amount of thermal bath. How do we initiate it? So this is why I've added the coupling to a photon or a dark photon. For small h, the equation of motion for the photon has this instability term. This is actually an equation of motion that Lian-Tao wrote down. This is the instability he's talking about when he was thinking about cosmological collider physics. If phi dot is turned on and phi is rolling, you get a negative contribution to the quadratic term, or to the equation of motion, the dispersion relation of one of the polarizations of this dark photon. And it runs away. It behaves tachyonically and starts putting any energy density into this field phi. If you then couple these two sectors, then that will cause reheating. It'll dump energy density, can dump energy density. When the number density of that photon gets large enough, it'll dump energy density into the non-abelian group, and the non-abelian group can produce friction on the rolling field. This then gives you all of phi's kinetic energy, or essentially all of phi's kinetic energy, rapidly heats the universe within a Hubble time, and this effectively stops motion of phi as phi dot becomes extremely subdominant to all the other energy density in the universe. And Hubble friction is then enough to stop it. The last step is to reheat the standard model. So one way you can reheat the standard model is, now that everything has been thermalized, forget this. Everything has been thermalized. For example, the dark photon we could mix with the photon. This is an example of a coupling of the standard model. And this will cause decays of, say, a heavy dark photon into the standard model sector, and you can come up with a rate based on that mixing parameter and the mass of A. And this sets the Hubble time at which you decay into the standard model, and thus it gives you a reheat temperature of the standard model. And these are free parameters. It also produces a direct coupling to photons. If you integrate out the dark photon, then this rolling field will also couple with an FF dual coupling. That'll go as 1 over F, but times the suppression of epsilon squared. This might be interesting. It will be later in the talk for observables. As long as F is greater than epsilon squared M Planck, then the dynamics of everything I've described don't change. However, if this coupling is big enough, then the whole story about how the cosmological constant evolves does change, but maybe even more interesting because we can do it with direct coupling to photons. So this is just a toy model or something that works, but there are many other variations that might be even more interesting. Now, we've tuned the cosmological constant. The universe is contracted and reheated. So now we have a universe that has a small cosmological constant, albeit negative, and it is contracting, and we want to start going the other way. Yes?
So why you have the different color in the figure? What the meaning in physics?
Red means you're expanding, everything is redshifting in a sense, and blue, violet means it's contracting.
So,
The color coding is just to remind you what direction the universe is going. That's all. All right. We need to bounce. We need the universe to turn around. And I'm going to describe a model of a bounce in effective field theory, meaning it scales below the Planck scale. Just as an existence proof in effective field theory that a bounce-like thing can happen even without sick matter. But I would say that most of you in the audience already believe that gravity causes bounces, because almost all of you believe that black holes decay via Hawking radiation. Maybe not all of you. But if you do, that is a situation in quantum gravity that you suggest that things fall in, hit a singularity or some Planck density, and at some very late times, geodesics leave that black hole. And if information is preserved, then you believe that there's evolution of stuff falling into a singularity, and then somehow, due to quantum gravity, coming back out. Here, I'm suggesting something that's going to be more calculable. I'm not attached to this version of a bounce, but it's simply to suggest that we have some biases about bouncing universes, but perhaps they're not exactly warranted. The reason the biases come about is if you try to do a bounce, if you take the universe and allow it to evolve via the Friedmann equations, you find that the only way to get a bounce, a double dot greater than 0, you find that either the energy density, matter density itself has to be negative, or W has to be less than -1. These sort of types of matter often display sicknesses, and matter then must, we call it, violate the null energy condition, which more generally can be described as take any null vector and contract it in this way with T mu nu. If that's less than 0, you violate this condition, and in Flat FRW, that's precisely one of these two conditions. So generally, we get concerned about this sort of matter. These kinds of things can have negative energy states, which means either vacuum decay or other instabilities. However, you can imagine some low energy effective theory having null energy condition violations and hope to avoid them with some UV completion. This is true about, for example, the strong energy condition, where naively, if the W is less than 0 for some sort of perfect fluid, you would naively guess that the scalar speed of sound squared is less than 0, or it's imaginary, thus an instability. However, the short distance physics for these type of fluids, which would be, say, domain wall networks or string networks or things like that, have additional modes, and the actual modes do not have these sorts of instabilities, say transverse modes or other things like that. So we might hope the same thing happens for the null energy condition, and there are places where the null energy condition is violated in a healthy way, namely in compact spaces. A compact dimension has Casimir energy, which violates the null energy condition, and positive spatial curvature, also a compact space, plays a role of violation, null energy violation, because it looks like a negative energy density in the first Friedmann equation. So if you had a compact universe, you could do it. We want to do it for a non-compact universe. And so our way out was to look at ways you can take converging geodesics and cause them to diverge. And if you look at the Ray-Chowdhury equation, which is the equation that describes how geodesics evolve, congruence of geodesics evolve, there are only two terms in this evolution that allow a converging set of geodesics to diverge, accelerate away from each other. One term is this omega squared, which is vorticity, and the other term is something that would require a violation of the null energy condition. We thought, let's attempt to use vorticity to cause a bounce and to allow null geodesics to go in and jump back out. This idea has been tried before, 80 years ago. This is the so-called Godel metric, where you have essentially just spinning dust and a cosmological constant, and there is vorticity everywhere in this space. And what you find, with vorticity you can tell in some versions, some coordinates, because time mixes with compact coordinate. In this space, you have a stationary universe, but you also have closed time-like curves. And this is the sort of sickness that you get with something with vorticity everywhere in the non-compact space. So we found solutions where you add additional compact dimensions, normal FRW compact dimensions, and you put the vorticity in there, and when you do so, you find that you can cure these sicknesses. You can plug in a bouncing universe, a bouncing scale factor, and ask what energy-momentum tensor you need in order to produce the Einstein metric in this case. Okay, lots of equations. So the short answer is, when you check the null energy condition in this case for rays in the 3+1 dimensions in the non-compact space, vorticity does combat gravity, and this mixing term between internal coordinates and time shows up and allows you not to have to violate NEC. If you look at null vectors inside the interior coordinates, then you find you do violate the null energy condition, but compact spaces, we can use Casimir. So we've shown at least an existence proof that you can get a bounce if you have compact spaces and some version of vorticity globally within that space. To get this curl everywhere non-zero in this space, you need 3 dimensions, compact, 3 or more, so it's a mess. There's another form of matter that we need that does satisfy all the energy conditions, and we're writing down just now, and hopefully will be out soon, a version of matter that'll actually do this for you. But the problem with these spaces is they're disgusting. They're 7-dimensional, they're a mess, and they're non-uniform. So they're not fun to work through, but this is at least an existence proof that such things should be possible. Now, that was the bounce. If you don't like that bounce, you can have ignored it. Go back to the rolling and tuning of the CC. So far, our model with the bounce naturally produces a small negative cosmological constant. They're roughly MeV to the 4th, but negative, from a larger capital MEV or 10 MEV to the 4th. And we might want to improve on this. But before we do, just want to say 2 reasons why this flavor of solution makes more sense to me. One is there's the Weinberg no-go theorem for the cosmological constant, which says that anytime you try to make the potential 0 and the first derivative of the potential 0, meaning a minimum, in the same location, you are required to fine-tune. But if v prime is equal to 0 in many locations, and if this is just a flat or linear potential, it's approximately 0 everywhere, then this fine-tuning doesn't exist. The other question people ask when you attempt to solve a cosmological constant problem is that the cosmological constant is tuned, let's say in the early universe, then don't phase transitions in the standard model give you another vacuum energy. But what we've done is we've inflated and cooled the universe to the standard model vacuum, and that's when we tune the cosmological constant. So when the universe reheats and we, let's say, unphase transition through all the standard model phase transitions that may or may not exist, then the final evolution of Big Bang cosmology down to what would be t equals 0 eventually for this universe is the vacuum that is tuned. So you make the universe ice cold, you tune the cosmological constant, and then you reheat it. And then you know that the vacuum of that field theory has the tuned CC. May have concerns about the fact that we need to evolve extended distances over this potential much, much larger than M Planck. Naively looks bad for things like the weak gravity conjecture, although in effective field theory, the weakest version of the weak gravity conjecture really is something about the Planck scale. And below that scale, there are effective theories that can produce what look effectively like very long field ranges, much bigger than M Planck. This was talked about by Ki Woon to some degree. And I have a discussion about it, but I don't have time, but I put the slides in so you can look at them later, but not for this discussion. We want to make it a fully viable model. The most important thing is that the cosmological constant today looks positive. It's possible that there is very low energy physics at the order of electron volts, for which there's a phase transition that takes much longer than the age of the universe to transition. And when we were rolling to tune the cosmological constant, we may have been in a lower vacuum that we are in now. So it is possible for very, very low energy phase transitions that we're not in the same vacuum, and this would be a way to add a little bit back of vacuum energy. But there's still a rolling field, and we would expect that rolling field to be in existence today. The models we have are sort of ugly scalar field theories for this, but there's possibly some confining groups, Yang-Mills groups, that produces what we want. I don't have time to describe how we get to higher cosmological constants, but there are terms, there are friction terms that one can add to use. Instead of Hubble friction, we can use couplings to abelian groups or non-abelian groups and get friction down here that allows the parametrics to change. So for a single field, we've gotten it up to 10 GeV, and we're working to see if we can do even better than that. But multi-fields, we can get it to significantly higher than the weak scale, and thus avoid things like even LHC bounds. Don't think I have time to talk about cosmology. What's my time? Okay. This is the timeline of the universe, of this story. Expansion for an incredibly long time, a contraction phase that roughly lasts the age of the universe, and then the expansion phase, another factor of a Hubble time today. We can ask about inflation in the sense that you want to know that this long evolution itself, can it be our period of inflation? It does make the universe insanely flat and homogeneous. It's a much longer period of inflation than we normally invoke. But we have to inflate down to incredibly small energy scales. That's far too low to start BBN. But with the bounce, we reheat, and that's why we contract. That sort of starts the universe. But the question is, does that contraction mess up homogeneity, flatness, etc.? It does not. But second question is, can you get the perturbation spectrum right with such a crazy low inflation scale? Standard inflation, written in terms of the co-moving horizon size and the scale factor, reduces the co-moving horizon size during inflation, and during normal Big Bang cosmology, the horizon size grows. So perturbations leave the horizon during inflation and re-enter at some time during Big Bang cosmology. Normally, of course, the Hubble during inflation is much larger than the Hubble today, but this is what a bouncing universe might look like. A long period of inflation, a contraction, a bounce, and a re-expansion, and now, which could be, in fact, even a smaller scale factor than it was during the period of inflation. So modes leave the horizon, bounce off this point here, following time evolution, bounce off this point here, and then re-enter the horizon now. So perturbations can actually enter the horizon, or enter at a larger value of Hubble, or a smaller value of the Hubble radius than when they left. And because this is a long period of inflation, they leave flat. Now, you can ask, can these perturbations grow during expansion? Because with such a low value of Hubble, the delta rho over rho is excruciatingly small. Possibly not. We're still working out the details. The scalar curvature may be conserved even during this contracting phase, but there may be other sources of scale invariant perturbations, the curvaton or thermal fluctuations during this period. They all have the same, every mode has the same contraction period, and so that growth period will be the same for all of the modes, giving us what looks like a flat spectrum. This is all very preliminary, and we're still working out the details. Now, most important, it's fun to come up with ideas to solve the cosmological constant problem. How do we know if it's true or not? I will very briefly describe the signatures. One is, of course, that if there's a rolling field, it should be rolling today. It has no minimum. And so if it's rolling today, you can ask what component of the energy density of dark energy is the kinetic energy. Current cosmological constraints set the kinetic energy component of dark energy to be less than 5%, but there'll be many experiments that will measure this better. There'll be first Euclid, other gravitational wave experiments. Could make a discovery, hard to rule out a lot of parameter space in this way. If phi couples to photons, say through the desire for friction or just for the fact that we know we have to reheat the standard model, that coupling to photons become very important. And in fact, a constant rolling field due to this coupling to photons changes the polarization of photons moving through it because it affects the different circular polarized modes differently. And so a rolling axion rotates the polarization of light by an amount delta theta, which is delta phi over f, from the time the light is emitted until now. And this is cosmic birefringence. It changes E modes to B modes in the CMB. There is a current limit from Planck and other experiments which says that cosmic birefringence of the CMB must be less than half of a degree, or about 10 to the minus 2 radians. That sets a constraint on our coupling to photons and the little correction to the dark energy equation of state of 10 to the minus 4. In a sense, they are just about now probing Planck scale physics. If the photon has a Planck scale coupling to some rolling field, they are testing it as well or better than just straight cosmology. And future CMB polarization measurements, say CMB4 like experiments, should get this number way down. And this then will be a very deep probe into rolling fields coupling to the standard model. The last thing I'll talk about is an idea we had for how to test a rolling field's coupling to fermions. For naturalness, we wanted a derivative coupling, and a derivative coupling to fermions in the non-relativistic limit looks like a gradient of phi dotted into the spin of the fermion. Now, that's interesting because as fermion moves through this background axion field, it will have a relative velocity, and that relative velocity will produce a gradient for phi. Now, our relative velocity is very small to the background, but if you put fermions in a ring and they go roughly the speed of light, there is no suppression. And grad phi in that frame is roughly phi dot. And phi dot is that contribution. It's the rolling field contribution to the energy density. Notice what this is. This is some background field dotted into the spin. This is like a virtual magnetic field. So a rolling background field relative to a moving fermion is an anomalous or new type of magnetic field that the fermion will see. So if you had an experiment where these fermions were moving roughly the speed of light at, say, a magic momentum, so that the polarization always points radially, then the effect of this fake magnetic field will be a precession of the spin out of the plane. And we look for that precession to measure or detect a background rolling field. There is an experiment being proposed by Yanis Samazidis and others. This is a proton storage ring EDM experiment. They're using exactly the same sorts of ideas to look for an electric dipole moment of the proton. But this same experiment can do tests of dark energy. Dark energy being a rolling field with a derivative coupling to protons. So to summarize, we've demonstrated a calculable solution to the CC problem if we assume a bounce, and I've given you an example of how you could do a bounce in effective theory. This is the only known solution that at least I know about it with no thicknesses all the way up to M Planck. The dynamical relaxation, like a 1D landscape in a sense, it's just a flat potential, but avoids therefore Weinberg's theorem, no-go theorem. And however, it has some deterministic dynamics. It doesn't require anthropics. So for the future, we look to have more details about a calculable bounce and embed it into this model. We'd like to see if you can get the perturbation spectrum that normal single field inflation gets. We can ask, are there better versions of this model or other types of ideas like this? But most importantly, are there more observables? And the experimentalists, we hope, will get to looking for this in more detail. And that's it. Thank you.
One question. Yeah, thank you.
So this, you say that the field, the axion field is still rolling,
Yes.
but you also need, at some point earlier, you need a upper lifting to become a positive CC.
Yeah, some
And
other field.
that upper lifting does not screw up the fact that this field is still rolling.
Yeah, this is some independent, so I shouldn't have used phi, let's call this chi. But this is some independent field, or some independent phase transition.
Something else give you the...
There's something else that has a phase transition. So there's a QCD phase transition, perhaps,
But this thing is itself is super protected. It's still rolling.
but the other one is still rolling because they don't couple only through gravity, and so that field has only derivative couplings.
Okay.
So I think because of time, let's move further discussion to the lunchtime. Let's have